All right, chemistry girls, I have some notes here to talk to you a little bit about how the Gibbs free energy change can depend on temperature. So you see our equation here, delta G equals delta H minus T delta S. The spontaneity of the reaction depends on the enthalpy change and the entropy change. This is a little graph I've drawn as if we were drawing a graph in math with the different quadrants. And let's imagine that our delta H values go along the x-axis and our delta S values go along the y-axis. If you think of it that way, we can identify these different quadrants that I've colored in with little faces. Here, in this quadrant, we would be looking at negative values of delta H, exothermic reactions, combined with positive values of entropy change. And you can see by my little faces that is a good situation. That means that the reaction would be a spontaneous one at all temperatures. Exactly opposite here with a sad face is the quadrant that would represent positive values of delta H, so endothermic reactions combined with decreasing entropy. Those are both not good in terms of spontaneous reactions, so these kinds of reactions are non-spontaneous at all temperatures. With the two yellow quadrants, you can see some happy and sad faces here. We're going to talk in more detail. This is where, as it says, this will depend on what the temperature is. To say whether the reaction is spontaneous or not, you will need to talk about exactly what the temperature is. The green section, and this is actually supposed to be red, these are all or nothing kind of situations. So we're going to look at the yellow ones in a little more detail. And by the way, there's a table on page 464 that shows this same information in a little bit different way. They don't draw happy and sad faces, but anyway, just to talk a little bit more about those two all or nothing quadrants. This is the green one, so remember this is where we're combining an exothermic reaction with a reaction that shows an increase in entropy or disorder. And if you look at it strictly in terms of mathematics, exothermic reactions have negative delta H values. T is temperature, remember, and on the Kelvin scale there's no such thing as a negative temperature, so temperature values are always positive. Increasing entropy, that's a positive delta S value. If you look at the mathematics of this equation, there's no way that the delta G answer cannot be negative. It's always negative, and that means that these reactions are always spontaneous. Mathematically that's true, and conceptually it's true because the exothermic process is a favored process. Increasing entropy, both of these things are natural ways. Things like to proceed in the exothermic direction, and they like to proceed in a direction that increases the entropy or disorder. So that's how that one works. Now, of course, the exact opposite would show up something like this, combining the endothermic reaction with a decreasing entropy. Both of those are opposite to the way that nature normally likes to proceed. An energy absorbing reaction, a reaction that decreases the entropy or disorder, becomes more tidy. Again, just mathematically, you would be putting in a positive value for delta H, a negative value for delta S. Temperatures are always positive, so if you think about this combination, this second term would end up being positive because of the subtraction. So therefore, the mathematical answer, always positive. These reactions are non-spontaneous. Sometimes you see this explained a little differently. The reaction is non-spontaneous as it's written or in the forward direction. That would mean, kind of by conclusion, that if we decided to make this go the other way, that reverse reaction would be spontaneous. But the positive delta G corresponds to the forward reaction as we read it. That one is a non-spontaneous reaction. Now, to look a little more carefully at those two kind of yellow areas where it was depending on the temperature, here's one of them. We could take the negative value of delta H. We could combine an exothermic reaction with a decreasing entropy reaction, something that does release energy but yet shows a decrease in entropy or disorder. If you look at the mathematics here, we'd be plugging in a negative value for delta H, but we'd also be plugging in a negative value for delta S. so that this second term of the equation, counting the minus, this would be a positive term. Well, here's how it works. If the temperature value is fairly low, then the negative delta H number will be greater than the positive term here, and therefore delta G would be a negative value at lower temperatures. Meanwhile, at higher temperatures, the opposite would become different. The opposite would be true. Now this negative delta H value, which hasn't really changed, but it's now less than this value, because as we keep increasing the temperature, we keep making this positive term greater and greater. So at some point, this positive term overrides the value of delta H, and our free energy change will now be positive, indicating a non-spontaneous reaction. On a graph, it might look something like this. At these lower values of, when the temperature is lower down here, closer to 0, that's where we can get our negative values of delta G, solving for the value here, the free energy change. Meanwhile, as the temperature increases past a certain point, this would become non-spontaneous. And mathematically, of course, this means that there is some temperature where the delta G value is exactly 0. We'll talk about this a little bit, but at that temperature where the delta G actually becomes 0 as it's switching from negative to positive, that indicates a situation known as equilibrium. And what that technically means is at that point, the reaction is equally likely to go either forward or reverse in either direction. So this is a mathematical fact that these reactions, I also think of it kind of conceptually though, because an exothermic reaction, remember, is one that releases energy. So if the temperature of the surroundings is fairly low, that energy releasing process can go okay, if you think about it. Meanwhile, if you really crank up the temperature of the surroundings, it's as if it becomes a little more difficult. The reaction is still trying to release energy, but yet there's a lot of heat and energy in the surroundings, so that's kind of working against it. Maybe that's a conceptual way to look at the same situation. Finally, here's the other it depends situation, combining our endothermic or energy absorbing reaction, which is not so great, with an increasing entropy, increasing disorder reaction. Mathematically, it would look like this. You would plug in a positive value for your delta H. You would plug in a positive value for your delta S. Temperature's always positives. So here we would be comparing the positive delta H value to this negative term here. If the temperature is fairly low, then that means that the positive delta H value will kind of win the math. It will be greater than the negative term here, and that will result in a positive delta G, positive free energy change, non-spontaneous reaction. Meanwhile, as the temperature starts to increase, then you have the opposite happening. The higher the temperature, the larger this term becomes, so that eventually this negative term will win, and the final answer for delta G will be a negative value, and the reaction will become spontaneous at higher temperatures. Mathematically it works, and I think conceptually, to me, remember, an endothermic reaction is an energy absorbing process. So if you try that in a fairly cool, low temperature environment, probably doesn't work so well. Meanwhile, if you suddenly place this energy absorbing reaction in a higher temperature environment, then suddenly it can work. There's enough, it's kind of as if the higher temperatures of the surroundings just help that endothermic process. Again, this is all summarized for you on page 464 in a slightly different way, but maybe you like my happy and sad faces.